Hello everyone, my name is Ilya and welcome to my bachelor thesis intermediate presentation. The topic of my research is real-time modern fluid simulation techniques for adaptation in game environments, with the research question being which real-time modern fluid simulation techniques perform best in terms of physical accuracy and computational efficiency. I chose 3 different fluid simulation techniques that seem to be the popular choice among game developers. The first one is basically the most straightforward approach that one can take, which is using a Unity built-in physics engine to handle the simulation. I represent each water particle as a rigid body with no friction. It's very slow, inefficient, inaccurate, and unpredictable. I use this mostly as an educational example of how not to do the simulation. However, it does have its own small-scale applications as well as advantages, like implementation, simplicity, easy debugging, and natural integration with Unity physics. People can also use it for quick tests of certain mechanics or simple 2D apps. The second method is based on the cellular automata algorithm. The system iterates over a grid and updates the fluid accordingly. The behavior of the fluid is defined by a set of rules. First, the water moves downwards, then it transfers a portion of itself to adjacent side cells, and finally, if it becomes pressurized, it can flow upwards. This approach is significantly more performant, scalable, and predictable. However, without a post-processing, it flows in a distinct grid-like pattern. This can reduce accuracy for certain applications. Despite these limitations, it remains a popular choice for sandbox games such as Minecraft and Terraria, and it is sufficient for most gameplay needs. The final technique is called smooth particle hydrodynamics. It represents fluid as discrete particles where each particle's physical properties are influenced by its neighbors and smoothed using kernel functions. It offers strong performance as it typically runs on the GPU and uses spatial hashing to reduce computational complexity. It also produces highly realistic visual results. However, it's difficult to implement fast, as it requires advanced physics, compute shaders, and complex algorithms. If you need an accurate and efficient water simulation, smooth particle hydrodynamics is an excellent choice. It is commonly used in simulators, scientific applications, and small to medium scale games. Criteria that I chose for a comparison include performance metrics like GPU and CPU consumption, frame rate and stability on different frame rates, also how well the simulation represents physical properties, visual appearance like surface smoothness, and detail preservation like splashes and droplet formations. I also evaluate time and effort that the implementation of each of these techniques might take, so reader can estimate the effort. I've done the implementation of all the techniques in 2D. I've started with the hardest and did the SPH first on the GPU. What's left to do is to implement all the techniques except maybe the first one in 3D, optimize cellular automata to run on GPU, and apply the chosen technique in a 3D game. For the progress in writing part, I've done the outline of what exactly I'm going to write about. I've read the theory and referenced it in the right place. I also started to do the comparison study for the 2D implementations. I have to structure the paper better, document the implementation, and also dedicate a few pages to theory about how to render the fluid in visually appealing way. My timeline has slightly changed since I drastically underestimated the complexity of optimization. If I want to make the fluid applicable, I can't run it on the CPU, and I'm very new to compute shaders and there is a lot to learn, not including the physics and other optimization techniques. Thankfully, the hardest is already behind and I just need to concentrate on the 3D implementation of what I already have in 2D. Thank you for your attention. Please ask questions if you have any.